Okay, let's talk about the polycondensation reactions. I think we will start with the difference between the step-cross polymerization and the chain-cross polymerization first. Okay? You should know what are the step-cross polymerization and what's the difference between step and chain-cross polymerization reactions in terms of the molecular weight, in terms of the rate of polymerization, in terms of the conversion percentages. Okay? So we will talk about the difference between the step and the chain growth. And you will know what are the degree of polymerization. Well, degree of polymerization is almost equal to the repeating units. You will know that the repeating unit of those monomers, but we will redefine the degree of polymerization reactions. If you know the degree of polymerization, then we will be able to calculate the molecular weights. Okay? And in order to have the, in order to get the high molecular weight polymer, we have to have a very high yield of the polymerization reactions. And for that case, in order to have the high degree of polymerization, we have to think about the requirements. We need to know about the several requirements. Okay, to break the equilibrium and to have the high yield. We should know about several aspects of the high degree of polymerizations. So let's talk about the classification of the polymerization reactions, first by mechanism, where you will, step-cross polymerization and chain-cross polymerization can be, different depending upon the polymerization mechanisms. Okay? So we will talk about this. You also knew that the condensation reaction and addition reactions. Condensation is different from addition reactions in terms of the production of the byproducts in the case of condensation reactions. Addition reactions just add the monomers so that you do not have any byproducts. So we knew that addition reaction and condensation reactions. Well, traditionally, step-cross polymerization is almost equal to condensation reactions. Okay, and there is no step-cross and addition reactions before, but that's not true. In the step-cross polymerization reactions, we have both condensation and addition reactions, whereas chain-cross reactions, you do not have any condensation reactions. You always have the addition reactions only. In the case of chain-cross polymerization reactions. So we can classify by the mechanism or by the type of the reactions. We also can classify this polymerization reactions by the bonding. Okay? Bonding such as radical or ions. Okay? The radical, if you have a double bond, this double bond might be broken into two pieces. Reactive sites, if your double bond will be cleaved homolytically, meaning that your electrons will be cleaved with the same portion to the two carbons, it will generate the two radicals from the one double bond. Okay? That's why we think the two radical formation from one double bond, so that the one double bond is regarded as a bifunctional because we produce two radicals. If you think about this double bond cleaved heterolytically, meaning that your electrons from two carbons will be moving to one carbon, and the other carbon is deficient in electrons, whereas the first carbon is rich in electrons. The rich carbon, electron carbon, is called anion. Okay, we call it as a carbanion, whereas the carbon with deficient in electrons is called carbocation. Okay, so you have both carbocation and carbanion from one double bond. So you have actually two reactive sites, minus and plus. So that's why we call this double bond as as a bifunctional. Okay, you can generate 2 radicals, or from 1 double bond, or you can generate both positively charged carbons or negatively charged carbons from 1 double bond. So anyway, we will talk about this radical reaction and ionic reactions. Okay? So from 1 double bond, if the radical is the most reacting sites for your polymerization reactions, we call that as a radical polymerization reaction. If the ions are the most, the promising, the active sites for your polymerization reactions, we call that as an ionic polymerization reaction. You can have both. In the case of ionic polymerization reactions, we have both cationic polymerization or anionic polymerization reactions. So you have several types of the polymerization reactions. So I will tell, these polymerization reactions in more detail, starting from condensation reactions. Okay? So in chapter 8, we will talk about condensation reactions. In chapter 9, we will talk about the Chang-Gross polymerization reactions, starting from radical reaction and ionic reactions later. Okay? Well, let's discriminate between the Stack-Gross polymerization and Chang-Gross polymerization in terms of the molecular weight and in terms of the rate of polymerization reactions. Okay? In the case of Stack-Gross polymerization reactions, growing chains. I think you saw your monomer. Okay, monomer will be reacting step by step. So you have a growing chain of your polymer, but you have many growing chains because you add the catalyst into the reaction medium. So growing chain react each other and increases your molecular weight. Therefore, molecular weight is slowly increasing, and the high molecular weight component will be only found at the end of your reactions. Okay? And this is the very typical the scheme for the Stack-Gross polymerization reactions, whereas in the case of Chang-Gross polymerization reactions, monomer molecules is just like a chain or just like a Lego. Okay, the monomer will hit the other monomer and so on. So the molecular weight will be increasing very fastly at the beginning, and the reaction rate is very fast. So high molecular component is found at the early stages or at the initial stages. So if you can draw the molecular weight versus the conversion, okay, conversion is what? The yield, okay? Your monomer, if the percent conversion is 0, that means that you do not have any reaction, okay? You only have monomers. If the conversion is 100%, it means that your whole 100% of your monomer is converted to polymer. So your molecular weight is increasing as you increase your conversion. However, the shape of the molecular weight increase is different depending upon the reactions. Okay? In the case of Stack-Gross polymerization reaction, we knew that it's very slow at the beginning. The molecular weight is Mn is molecular weight, and it's very slow. But at the final stages, you increase your molecular weight. Okay? Whereas in the radical polymerization is one of the Chang-Gross polymerization reactions. Therefore, in the case of radical polymerization reactions, your molecular weight is further increased compared to a Chang-Gross polymerization at the same conversion. But the rate of increase is quite slow later. In the later stages, your slope is quite decreasing in the case. So this is very typical for Stack-Gross and Chang-Gross polymerization, particularly the radical polymerization reactions. Now, I have here some kind of azeotropic line here. Okay, this is very simple, similar to your distillation curve in chemical engineering, and this what you can see here, the rate of conversion or percent conversion is equal to the molecular weight, and it's increasing very linearly, okay, not exponentially, but linearly. We call this as a living polymerization reactions. We will tell you, I will tell you what are these living polymerization reactions, but I told you that ionic polymerization reactions, okay, particularly anionic polymerization reactions. Anionic polymerization reactions are called the living polymerization reactions. Okay? What it is that if you add the monomer and state your monomer with the initiator into the oven, and several hours later, your monomer will be added to your polymeric units. So the monomer is becoming polymer, and at the end of your chain, you have anionic species. Okay, anionic species still alive in the reaction vessel, and later, if you add some more monomer, then it will be adding it as well. So there is no loss unless you have water vapor or water into your the reaction system. So water is very much causing the termination reactions, but except the presence of the water, you will be able to make the living polymerization reactions, and step by step. Okay? So we call that as anionic polymerization reactions, but be careful about the water in the case. Okay? If you have water, then it just terminates. Anyway, without the presence of the water, you can, if you add some amount of the monomer, it will be added to become a polymer, with a given monomeric units. So we will talk about it later in chapter 9 of both of these, but I will we can discuss about the step-cross polymerization first in this chapter. Okay, so in the case of step-cross polymerization reactions, we knew that we have both condensation polymerization reactions and addition polymerization reactions. But I will discuss the real difference between the condensation reactions and addition reactions first. Okay? Condensation reactions, the typical characteristic of this condensation reaction is the formation of the byproduct. Okay? If you have any byproduct, we call that as a condensation reactions. For example, you have adipic acid. Okay, you have adipic acid. So one of the structure that I have given you is what are the structure of your what's that? Polyadipamide. Hexamethyl adipamide is this one. Okay, here. You have adipic acid and hexamethylene diamine reacting with together to become hexamethylene adipamide. Okay, adipic acid or terephthalic acid or any other acid contains bifunctional units, and the diamine, the amine group, will attack this carbonyl, and you form the byproducts. Hydroxyl, water, and hydrogen will form the water here. Okay? So you have a byproduct, which is water in this case. Okay? If you don't have any byproduct, we call it as addition polymerization reactions. Okay? Just like in the case of vinyl polymerization reactions. Now this is you have a methyl group here, okay, methyl group, and you have a carboxylic acid. So you can say that you have a methyl group here, okay, methyl group, and you have methyl group. We call this as a polymethyl methacrylate. Okay? We have the similar structure here, but you do not have any methyl group. You have a hydrogen here, okay? And you have a methyl group here. We call this as a methyl. Well, you can start from this reaction. This is acetyl group. This is vinyl alcohol. If you react vinyl alcohol with the acetic acid, you form this polyvinyl acetate. Okay. We call this as a polyvinyl acetate. Okay. So the chemical structure is coming from. Anyway, you can form this type of polyvinyl acetate or polymethyl methacrylate from your monomer, vinyl acetate or methyl methacrylate, so that you can form the polymer by the addition polymerization reactions. You do not have any byproduct here in this case because your double bond will be broken into two pieces, which might be radicals or ions, okay, carbanion or carbocations. Carbanion or carbocation or radical can be formed depending upon your monomer and also the catalyst. Okay. What kind of catalyst that you are using will be a determining factor of your the mechanism for your the polymerization reactions. It could be you can add your ionic monomer, ionization the monomer, or radical forming monomer are the very important aspect of your determination of your polymerization reactions. Okay. So step-course polymerization again. At the beginning of the chapter 1, we discussed about the history of the polymers, and I have emphasized the very important person, Carrodus, and he was a professor at Harvard University chemistry department. He was an assistant professor at the time. He was quite young, and he announced that inspired by the Professor Staudinger, who suggested the macromolecular hypothesis back in 1925, he synthesized several polymers using the step-course polymerization reactions. And he synthesized first of all, the propionic acid with the ethanol. Okay, you have a hydroxyl group, or you have a carboxylic acid and the alcohol. If you add in this two reaction, the monomer, if you add the sulfuric acid as a catalyst, then it will take the water out to form the ester. Okay, so you have ethyl propionate. Okay, this is the ester, and you form the 1 mole of water coming from these reactions. Okay, but you have an ester, but there is no further reaction after forming this ethyl propionate. Okay. However, but Carrodus was thinking about the reaction where if you have 2 carboxylic acid instead of 1 carboxylic acid, and if you have 2 alcohol instead of 1 alcohol, you may form some sort of a cyclic ester, the diester, and this is very typically known at the time. Okay? There was no polymerization reaction, but you form some sort of the diester. Okay? However, he thought that maybe if you add two bifunctional monomers getting together, it could be a viscous solution. Okay, viscous solution rather than just a small low molecular weight components, and you form the multifunctional the polyesters instead of just a simple ester. So just by changing the monomer from monofunctional monomer to bifunctional monomer, it will be a very viscous solution with high molecular weight component rather than very simple and very definite molecular weight, low molecular components. Okay, so he found that he published an article in 1929 in Journal of American Chemical Society. Okay, and he said that intermolecular condensation requires as a starting material components in which at least 2 functional groups are present in the same molecules. Now, that means that if you wanted to make a polymer, you have to have a bifunctional monomers. At least 2 functional groups present in one monomer is a very essential requirement of the polymerization reactions. Okay? So we knew that the bifunctional acid here, which is a dicarboxylic acid, or diol. Okay? Okay? Again, bifunctional group is very much essential for your polycondensation reactions. Okay? If you have only 1 functional group instead of 2 functional groups, it just terminates your reactions because there is no further, extension of your functional groups. So if these 2 will be reacting, you form ester, but at the end of your chain, you still have an active component, active functional group. At the one end will be a hydroxyl group, and the other end will be the carboxylic acid group. If you add the equal amount of your the monomers, okay. But if you add excess amount of one monomer, in other words, now we have 1 mole here. If you add 2 mole of the alcohol, after some time, what happens is that you have both ends will be hydroxyl group, okay? So both ends. In other words, one end will be the hydroxyl group, and the other end will be hydroxyl group as well. Okay? If you have those conditions, then you do not have any further reaction, polymerization reactions. So this is the particularly very good way of determining your molecular weight. In other words, by changing your molar content, you can calculate the exact amount of your the molecular weight by knowing the molar content. Okay? However, if you have equimolar contents of the 2 monomers, your molecular weight will be infinite. Okay, principally, basically, or theoretically. Anyway, we will talk about this aspect, controlling the molecular weight, later on. But anyway, what Carolus was emphasizing was that at the time, the polycondensation requires at least 2 functional groups in one monomers in order for these monomers to become polymer. And this concept was extended by Paul J. Flory. At the time, the Flory was a professor at the Cornell University, and in the 40s and 50s, he thought that the reactivity of the functional group, in our previous case, will be carboxylic acid or hydroxyl group. Anyway, the functional group reactivity is not correlated with the complexity and the size of the molecule with the functional group. Well, this terminology or this statement might be a little difficult for you, but I will show you what it is. Okay, we have alcohol. Okay, you should have a diol. Okay, in other words, you should have 2 alcohol groups in one monomer. Okay, if you have a long chain instead of a small chain here in this al, but at the end of the chain you have 2 functional groups. Size of the alcohol does not bother the reactivity of your functional group, reactivity of your alcohols, and or the complexity. In other words, reactivity of your alcohol and reactivity of your carboxylic acid to form the polyester doesn't really matter. Okay? So size or complexity of the functional group does not really bother the polycondensation reaction, is the concept at the time suggested by Flory, okay, later on. So this concept could be applied and could be a very useful the reaction. And if you think about this, the isocyanate, this is the polyisocyanate, and diamine will form the polyurea. Polyurea will be now again, this functional group is called amide, right? If ever one more imine group, we call this as a urea group. If you have amide and ether here, we call this as a urethane. Okay, so if you have these functional groups in your polymeric units, you can just put polyurethane, polyamide, polyurea. Okay? And polyurea, polyamide, polyurethane are just a general name. Okay? That doesn't specify the type of your monomer in your the polymers. So this is just a general name containing the functional groups. The al here, R or al prime, are the different type of your isocyanates or diamines. So if you just change your diamines or diisocyanates, you can form different type of polyurea, different type of your polyurethane, different type of your polyamide in many cases, if you just change your monomers. So the size of your al or size of your al prime or complexity doesn't really matter for your polycondensation reactions, as suggested by Paul J. Flory. Now, this concept can also be applied to the chain-cross polymerization reaction as well. Okay? Complexity or size of your the monomer doesn't really matter into the reactivity of your functional groups. For example, polyolefins, polyethylene, polypropylene, stuff like that, or polyvinyl monomer. Vinyl monomers, ethylene, propylene, vinyl chloride, vinyl fluoride, or unsaturated monomer containing double bonds. If you have two double bonds, one double bond, or triple bonds, those were called the unsaturated monomers. You can form such as polyethylene, ethylene. In this case, the ethylene will first meet with the initiator, okay? Initiator. In the chain-cross polymerization reactions, there are three very important steps. Okay? I think you'll learn these steps in your organic chemistry course. What are those? Three very important steps. Initiation, propagation, and termination, right? So the initiation requires initiator. What type of initiator that you're using will determine whether this reaction is a radical reaction or ionic reactions. Anyway, we can assume that we have initiator forming the radicals. So we will talk about this in a minute. But termination requires some of the terminator, or the radical will meet each other to form the dead end the molecules. Anyway, we can talk about this initiator. Initiator may have a radical. So radical will attack this vinyl monomer, okay, and form the two radicals, so that you have the one of the radical from this double bond will meet this radical here from the initiator, and you form the covalent bond. Okay, and the one more radical from your double bond just stays state right here, okay? And this is the initiation step. Okay? Now, in the next step, which is the propagation step, you will meet the one more the monomer, okay? And this radical will attack the double bond and form the similar reaction. So it forms, it goes on and on, okay, on, and you increase the molecular weight. Here, the radical will attack this double bond, and this double bond will be cleaved to form this, high molecular weight components, right? So the double bond here is regarded as bifunctional, as I said, because from one double bond, you form two radicals. So one radical will be contributed to form the covalent bond with the initiator, and the second radical is just to stay right there, and which will be later used to attack the other monomer, okay, to form the polymerization reactions. If you have a triple bond, what are the functionality? Yes, tetrafunctional. If you have a triple bond, triple bond, this is regarded as tetrafunctional. Okay? So this is the equal functional group reactivity concept, and this equal reactivity functional group concept can be treated as in two ways. First of all, thermodynamic approach, and the second one is kinetic approaches. I think we have already discussed about the thermodynamic concept, because you knew that Gibbs free energy of polymerization reactions here in this case will be touched upon, but we have already talked about Gibbs free energy of melting, okay, in chapter I think 5 or 6. Now, if you have a Gibbs free energy of the polymerization here in this case, you only change the subscript here, should be negative in order for the polymerization reaction to be proceeded. Okay? We call this as spontaneous polymerization reactions, but in order for a polymerization to be thermodynamically feasible, delta GP should be negative. If delta GP is equal to 0, we reach an equilibrium, right? We reach an equilibrium. If the delta GP is positive, then polymerization reaction is now thermodynamically possible. Okay? So we have Gibbs free energy definition is equal to enthalpy minus T times entropy, and we all knew that this equation is a basic understanding of the polymerization reactions, and you knew that the Gibbs energy of a polymer or Gibbs free energy of monomer difference is regarded as a Gibbs free energy of polymerization reactions, and we can say that delta HP minus T times delta SP, where delta HP is enthalpy change per the monomer units, whereas delta SP is regarded as enthalpy change per monomeric units. Now, again, if we summarize delta GP, if the delta GP is negative, then the polymerization reaction is spontaneously feasible. Whereas if the delta GP is positive, then polymerization is not possible. If the delta GP is equal to 0, your reaction is in equilibrium. Okay? So think about if you have a diacid and alcohol, diol, reacting together to become polyester. I told you that the arrow of your reaction is going from your left-handed side to your right-handed side. However, if it's in the equilibrium, then there is a backward reaction too, so that it reaches, you have two arrows. One arrow from left to right, the other arrow from right to left. So that's the situation where you have the equilibrium. Okay? There is no further polymerization reaction at the equilibrium. So the molecular weight is limited in the case of equilibrium reactions. Polycondensation reaction is an equilibrium reaction. Okay? so that it will always limit the molecular weight. However, if you break your equilibrium, okay, if you break your equilibrium by removing your byproduct, then the reaction will go from left to right. So arrow will be moving. So you can form the polymer by removing your byproduct and to break your equilibrium. Okay? That's the trick to make the polymer in your equilibrium reaction, which is a polycondensation reactions. If delta Gp is equal to 0, that means that you have delta Hp minus T delta Sp is equal to 0. At that situation, equilibrium situation, your T is defined as delta Sp divided by delta Hp divided by delta Sp. Okay? So delta Hp and delta Sp has some ratio, but at that situation, delta Gp is equal to 0. Okay, equilibrium. So at that equilibrium the condition, whereas the temperature at the equilibrium reaction is called the sealing temperature. Okay, sealing temperature. Sealing means the 천장. Sealing. This is what we call the sealing. Sealing blocks your sky with your interior, the pot. If you wear the hat, it seals from your sky or sunshine to your body. So sealing means that it just reaches some sort of equilibrium in terms of the thermodynamic terms. Okay, the other approach, what we call is a kinetic approach, is the condition where the delta negative Gibbs free energy change does not really matter where the polymerization reaction occurs. Okay? That's the essential part of your polymerization reactions anyway, but we have to have a functional group, or we have to have an initiator, we have to have the right temperature. Okay? Those are very important for your the polymerization reactions, other than the negative that gives it free energy of changes. So we will tell more about this kinetic approach later on. Okay, let me introduce the several ways of the esterification reactions. In the polycondensation reactions, we have a very typical reactions, which is called esterification, so that you can form the polyester, or amidation, polyamide, okay, or you can form, some other isocyanate, the polyurethanes, addition reactions, and so on. So I will, describe what are those reactions. You can form polyester by ester interchange reactions. Perhaps you knew polyester, but perhaps the ester interchange reaction is not quite common for your understandings. Okay. Again, in order for the polyester, you have to have a bifunctional groups in one monomer. In the first monomer, we have a diol, right? If you have a diol, we have to have a diacid. However, in this case, we have a diester instead of diol. Okay, diacid is not present here, but you have a diol already. This diol is the same as diacid, but the reactivity is a little different. Okay? But the reaction mechanism is the same. It's a nucleophilic substitution reaction, so that you're in the electron-rich oxygen. You have 2 electron pairs here. Electron-rich oxygen will attack this carbonyl, so that the carbon and oxygen bond, which is very weak bond strength, will be broken here. Okay, so this O will attack here and will be removing. So byproduct will be R, O, and H, which means alcohol. right? So from this reaction, you can form polyester, but the byproduct is alcohol instead of water. Okay? You form the polyester, but you form the byproduct, which is alcohol. Now, what's the difference between the water and alcohol? Yeah, but in terms of boiling point. Boiling point of water is what? 100 degrees C. Alcohol is low. Yeah, it could be 70 degrees C or 60 degrees C, depending upon your how many carbons you have in your alcohols. Now, I told you that this polycondensation reaction is an equilibrium reaction. So in order for your reaction to be proceeded from left to right to form the polymer, okay, you have to remove your byproduct. If you have a low boiling point, byproduct, it will be easily remove your byproduct in the case of your low boiling point byproduct, right? So this reaction, which is called ester interchange reaction rather than esterification reaction, is much easier to make the polyester rather than using diacid as a monomer. Okay, so in industry, in order to make the polyester, they use this ester interchange reaction rather than just a simple esterification reactions. So they first form the ester and reacting with alcohol later to form the polyester, because this alcohol is easy to be removed compared with the water removal. Okay. Now, this reaction requires high temperature. The temperature is typically from 150 degrees C to 250 degrees C, and you need a little bit of vacuum. Okay, vacuum, because water or the alcohol, although boiling point is about 70 degrees C in the case of ethanol or methanol, but you need to efficiently remove your byproduct to increase your molecular weight, because the reaction arrow, the arrow of this reaction should go from left to right. But we have some other reaction, which is called the Schotten-Baumann reaction, so that your reaction scheme or formation of polyester or polyamide is proceeded at room temperature. At room temperature, and I will show you, and also perhaps you will conduct the experiments in the dance floor with the energy experimental cases. But I will show you next time to form the polymer at room temperature by mixing this monomer together. What it is that you have a diol or you have a diamine reacting with the acid chloride rather than diacid or ester. This acid chloride is much more reactive than the diacid. Reactivity is very high. So the alcohol or amine group will attack this carbonyl, and you form the byproduct, which is HCl in this case, okay, rather than alcohol. This reaction is very fast, so we call this as a Schotten-Baumann reaction. Okay? And I will show you, I will bring the diamines, and I will bring the diacid, and I will put it together to form the polymer. This reaction is called the Schotten-Baumann reaction, following the scientist who found this reaction. Third example are the amination by the thermal dehydration of the ammonium salt, where you have adipic acid and hexamethylene diamine. Okay, you form the nylon 6,6, right? which is polyhexamethylene adipoamide. But it's not these two monomer where the amine will attack this carbonyl so that you form the water as a byproduct. But it's not very simply occurred in one step. So this is the two-step reactions. First step requires the formation of the salt at low temperature, below 100 degrees C. And later, as you increase the further the reaction temperature up to about 250 degrees C, then you form, hexamethylene adipoamide with the formation of the water as a byproduct. Okay? This reaction is almost the same as the esterification reactions, so that you have to remove your water in the second step because this reaction is already been the equilibrium reactions. If you do not remove this water, it will go back so that you reach an equilibrium. Okay? So efficient removal of your byproduct is very essential to form the hexamethylene adipoamide polymer, or nylon 666. Fourth example of the polycondensation reaction or the step-cross polymerization reaction is the polyurethane or polyurea formation. Okay? Isocyanate, N double bond, C double bond O. This functional group is called isocyanate. This isocyanate is also very reactive. Okay? You have a carbonyl, and you have a double bond between the nitrogen and carbon. So this point is an attacking point from your nucleophiles. So when you have an alcohol or amine group, the alcohol will attack this carbonyl, and it opens this bond, and the hydrogen will be attached to this nitrogen without forming any byproduct. Okay? Or if you have an amine group, instead of alcohol, this will attack this carbonyl, and for the same analogy, you open this N double bond C, okay, and N will form a amide group, whereas one more hydrogen will be attached here to form the urea. Okay, if you have alcohol, it will form urethane. If you have an amine group, it will form urea. Okay, so depending upon your monomer, depending upon your functional group, you have two different polymeric systems. Isocyanate is very reactive, as I told you, and isocyanate requires very careful storage systems. Okay? If you have a water, it will attack this carbonyl so that the isocyanate will be broken. Okay? You do not form polymer, but the water vapor will be an attacking medium to isocyanates. Isocyanate is very typically characterized in IL at the 2,200 reciprocal centimeter. Okay. This typical characteristic peak is very intensive in the case of isocyanates, okay, in your IL system. At this 2,200 reciprocal centimeter, you can also found, if you have a CN group here, or in acrylonitrile, the CN group can be found at the same wave number. Anyway, this is the strong peak. So if you have isocyanate, you can find that peak at the 2,200. If you do not have any isocyanate, after forming a polymer, your intensity will be much more decreasing. So after polymerization reaction, you should not find this N1C-O by looking at the IL, the peaks. Okay. Now this polycondensation reaction or stack cross polymerization reaction is a very well studied reaction, well characterized polymerization reactions. Okay. If you have a phenol, this is what we call the phenol or phenol, and formaldehyde. Okay, formaldehyde. This is aldehyde, right? And you have a hydrogen. What we call is formaldehyde here. Or if you have a methyl group instead of a hydrogen, we call this as acetaldehyde. Okay, so COH or CHO is called the aldehyde. This COH is very characteristically characterized because you have a carbonyl group. Okay, this carbonyl group can be found around 1700 reciprocal centimeter. Okay, but depending upon your carboxylic acid or carboaldehyde, we have a different shift. Anyway, you can take a look at the 1700 in the case of aldehydes. Now, formaldehyde and phenol has one hydroxyl group, and you have a formaldehyde. What happened? Can this be the polymer from phenol and formaldehyde? Yes. How come? We need to have at least two functional groups present in one monomer. But what are the functionality in this case? Yes, you can form the polymer, but why we have functionality? What are the functionality here in this case? Electron density. Yes, electron density is what? What are the electron density? If you look back your organic chemistry textbook, if you have alcohol, phenol, there are some reactivity directing sites, right? So if you have a hydroxyl group, it will be ortho para directing groups, right? And if you look at the aromatic reaction, back in, I think, chapter 14 or 15, then you can take a look at what are the directing group, whether it could be ortho para or whether it could be meta directing groups, right? So in this case, we have our ortho and para group directing reaction. So this 1, 2, and 3 position are regarded as active sites. So formaldehyde can attack these 3 sites, and it becomes polymer, something like this. So it will be a cross-linked polymer rather than linear polymer. Okay, if you have bifunctional or functionality of 2, you can form linear polymers. But if you have a functionality greater than 2, 3 in this case, you can form network polymers or cross-linked polymers, right? And this is why the bakelite was formed. So Bakeland, back in 1907, he found the first plastic, and insulating plastic called the bakelite was formed by just putting formaldehyde into your phenol solution and mix it up and heat it up. You form the unsoluble, unmeltable cross-linked structure of your bakelite plastics. which could be used to your insulator of your the socket, okay, electrical sockets. So Carodus. So this was the Carodus, the concept, and I would like to introduce you about the Carodus equation. Carodus was not alive, but he died in April 29 of 1937. And he was born in 1896. So in 1929, he was about only 35 years old. Okay, at the time he published an article, the functional group concept in Journal of American Chemical Society. About 7 or 8 years later, he suicided himself. At the backyard of the DuPont station in Delaware. But during those 6 or 7 years after publication of Jack's article in 1929, he suggested the very important concept or equation, which is called the Carodus equation. Carodus equation is very simple. If you look at the physical chemistry textbook or reaction engineering textbook, you can understand very easily. Okay? What it is that you need to know the initial concentration of your monomer. And if you know the conversion or extent of reaction, P, then you will be able to find the monomer concentration at time T. Okay? At a given time, after some time later, you will be able to find the concentration of your monomer after reaction by knowing the monomer concentration and the extent of reactions, or post conversion. Okay? So this is very simple equation where the C is equal to C0 times 1 minus P. Okay? In your physical chemistry textbook or reaction engineering courses, this is just you can just replace the C with M, where in this case is a monomer. So degree of polymerization, okay, degree of polymerization, dPn, is equal to the initial number of your monomer, or initial mole fraction, initial number of molecules in your system, divided by the number of molecules after time t, okay, after reaction, which is defined as n. Okay? If you replace n with m, it's about the same, okay? So that m is equal to m0 times 1 minus p could be replaced here in the denominator, and it will be 1 over 1 minus p. So dPn is simply 1 over 1 minus p. So if you know the extent of reaction, you can calculate the degree of polymerization reactions, or number of repeating units, here in this case. Okay? So this is called the Carodus equation. Now we can take a look at the extent of reaction, assuming that you have 0 and dPn is equal to 1, meaning that you only have a monomer. Okay? If the extent of reaction is about 0.5, you have dPn of 2. Only 2. After 50% of your monomer was converted to and participate in the reactions. Right? If you increase your P up to about 99%, meaning that your 99% of your full monomer out of 100, okay, participate in the reaction, what happened with the degree of polymerization reaction? dPn is only 100. And I told you that in order for the polymer to become regarded as a polymer, dPn should be over or close to 200, right? So 200, if you wanted to achieve the dPn of 200, P should be 0.995, right? So 99.5% of your monomer should participate in the polymerization reaction in order for this molecule to become regarded as a polymer. It should be very, very efficient. right? That's why if you go back to your percent conversion versus the molecular weight, step cross polymerization reaction is following this line, right? So molecular weight should be over 99.5% in order to achieve your, the decent or reasonable molecular weight. Okay? And this could be described by simple Calculus equation here. Okay, next time I think we can just follow the little bit more complex, a little bit more complicated reactions, which is regarded as modified Calculus reaction by knowing the functional groups. If you have if you know the functionality F, we assume that functionality is equal to 2. But if you have a complex functionality, meaning that in the case of phenol, you have a functionality of 3 instead of 2, right? So we wanted to generalize the Calculus equation by knowing the mole fraction and functionality. So this equation will be a little more complex, but simply, if you know the extent of reaction, then you can calculate the DPN. Okay, so. Okay. If not, then I would like to see you on next Wednesday. Okay, next Wednesday.